Okay guys, so today we're going to go ahead and do 5.7 integrals that result in inverse trig functions. We have three formulas that we're going to deal with. I'm going to prove the first one to you. What I'm going to prove is that the integral of dx over the square root of a squared minus x squared is equal to the sine inverse of x over a plus c. So I'm going to do it for x because it's easier, but remember that all we have to do to replace the x by u is put a du there in case that we have another function. So here's the proof. The proof is really easy. You're not responsible for it on the test. It's just to show you how it works. So I'm going to let y be equal to the sine inverse of x over a. Okay, so I'm letting it be this. And what I'm going to show now is that if I take its derivative, I'm going to get this right here. And so that's going to prove that this is the antiderivative. Okay, so now, because of the definition of the sine inverse, what we have is that the sine of y is x over a. And so x is equal to a sine y. It's important to remember two things here. First, that the sine inverse, when you put it in, your range is going to be from minus pi over 2 to pi over 2. That's going to be important in a minute. The second thing that it's important to remember is that a is a constant. This right here, I'm going to refer to a little later when I do another substitution in a different direction. Okay. Next, I'm going to take the derivative with respect to x. So we find dy dx, so to speak. Okay. So we're going to do implicit differentiation, and what we have is that now a cosine y, because we're differentiating with respect to x, we get dy dx here is equal to 1. It's dx dx, but that's equal to 1 anyway. So then, what we know then is that dy dx is 1 over cosine of y. Now we somehow have to make that look like this. Okay? It's not going to be incredibly hard. So here's what happens. Again, remembering that when y is equal to, or an element of rather, minus pi over 2 to pi over 2, which is where this is going to happen, the cosine of y is non-negative. So without loss of generality, we're going to use the Pythagorean identity, and we can drop the plus or minus because we know that it's going to be positive. We know that the cosine squared of x is equal to 1 minus the sine squared of x. You may remember that one as sine squared plus cosine squared equals 1, but it doesn't really matter. We can solve for it just as easily. So what we know then is that cosine, because it's positive, we can take the principal square root and we're going to get 1 minus sine squared of x. Okay? So now we're going to make a substitution. Remember we had 1 over a cosine y. I dropped the a over here. I'm sorry. Was dy dx. Okay. Now, what are we going to do with that? We're going to replace it with this right here. And what we have is that it's going to be equal to, now 1 over a square root of 1 minus sine squared of x. Okay. Now, bringing the a inside, all I have to do is square it. So what I have is, that's going to be equal to 1 over the square root of a squared 1 minus sine squared of x, which is going to give me 1 over the square root of a squared minus a squared sine squared x. Now, remember that actually, are these all y's? These are all y's. I apologize profusely. These guys are all y's, right? Well, then going back to this thing, x is a sine y, so what we get is 1 over square root of a squared minus a sine y squared, and that's going to give us that 1 over square root of a squared minus x squared. Okay, using this right here. And so now we've shown that 1 over a squared minus x squared under the square root is indeed a derivative of the sine inverse of x over a, and so necessarily the antiderivative of the 1 over a squared minus x squared is going to be sine inverse of x over a plus the general constant c. Now that's the proof. We're going to use all three of these formulas. I apologize for replacing the y's with x's somewhere in between. That happens to me a lot. You guys know that, so you're probably used to it. Anyway, so that's it for now, and next we're going to do some examples. Okay.